Optimal health for high performers. This is the Health Upgrade Podcast with Dr. Navaz Habib.
Welcome to the Health Upgrade Podcast, everybody. Thanks for joining. We're excited to have you here today. Our topic today is very, very scientific, heavy, and wonderful. And it's something that I think as we go through, it's really going to open your eyes to understanding the immune system, how we develop, how the immune system has been misunderstood for quite some time, and the cells that are actually required for our homeostatic optimal function. And that is the macrophage. And we're excited to talk about it. We're going to dig into understanding its role in development, in homeostasis, in inflammation, as well as what we can potentially do to control these. But we want to talk about the macrophage, all the different types of macrophages within the body, and just to understand why these cells function the way they do, why they're super important. And joining me again to talk about this particular cell and this very important topic is JP Errico. Thanks for joining today.
I'm excited. This is one of my favorite cells in the body, and I look forward to talking about it.
I love it. So we're going to jump right in. I think it'll be a great conversation today where we're going to talk a little bit about everything that has to do with the macrophage.
Absolutely.
So why don't we begin at the beginning, I think is the easiest area to begin with, understanding what a macrophage is and where they show up through our development, through our younger lives, through to our older age, and the function of what they do. So let's go through a timeline, I think, to begin.
Sure. And that's a great way to do it because macrophages show up extremely early in gestation. In fact, let's start right at conception. The sperm and the egg meet, and each one brings 23 chromosomes so that you get 23 pairs of chromosomes. And that first initial cell divides several times, basically reproducing itself in smaller versions of the same cell until it gets to about the size of 8 or 16 cells, at which point it starts to change its structure. It's beginning to morph into the structure that will ultimately be able to develop a full human being. And that first stage is called a blastocyst. It has about 32 cells, and it binds to the side wall of the uterus, and it begins to get nutrients. The analogy that I like to use is it's sort of like building a building. You've got a plot of land, it's got vegetation on it, it's not even connected by roads to anyone else, and you've decided you're going to build a skyscraper on this building, on this piece of land. And so the first thing you need to do is sort of prepare the land by removing the vegetation. And the first thing you do is you sort of stake out where the elevator shaft is going to be, where the foundation, the corners of the foundation are going to be, et cetera. And that's the very first stages of development. It doesn't look anything like a skyscraper. It's not like a tiny little skyscraper that's slowly growing. It has no resemblance to a skyscraper whatsoever. But the interesting thing is it has to be connected into the mother. It has to be connected back in so that you can bring all the nutrients and other things. You know, when you're building a building, you need to bring in the iron girders, you need to bring in the cement, you need to bring in the electrical wiring and the plumbing and all of those things. But the first thing you need to do is you need to bring in the people that are going to be able to build that building. Because the builders, the workers, the construction crew, all of those people have to be present. They're not parts of the building themselves, but they do all the work. And that's what the macrophage is. A macrophage is a worker that builds the building. And so they're brought in very early. By day 7 of gestation, you're seeing the preliminary stages of macrophages growing in that little ball. And some of them actually migrate into the placenta. Those are called Hofbauer cells. And that version of a macrophage is there to maintain an anti-inflammatory environment. Because if you think about it, one of the roles of the immune system is to basically get rid of non-self. And a mother who's going to be, having a baby growing inside her has to be able to tolerate non-self. I mean, there's no bigger non-self than another human being that's growing inside. And so that non-self risk has to be suppressed, that response to non-self. And the Hofbauer cells, which are part of that growing being inside you, has the ability to suppress that inflammatory response. It's an anti-inflammatory job that it's doing. It's also coordinating, bringing the blood vessels to the amniotic sac. It's helping to make certain that the right nutrients are being brought in. It's a coordinator of logistics, if you will. It's making certain that all the construction materials are getting to the site. There's also
much like a project manager for the site where the construction is occurring, right?
Exactly. And that project, another group of project managers or general managers, if you will, sit inside another structure that's growing really in parallel with the embryo is the yolk sac. We think of yolk sacs as like, that's inside an egg. That's what it is. It's an egg. And so what we have is a yolk sac that sits outside of the growing embryo. And inside that yolk sac, there's another set of subcontractors, if you will, in terms of the building analogy. And that set of subcontractors are a first wave, a second wave, and even a third wave of macrophages that are entering into that embryo to build it. And we've talked on one of the episodes, we talked about neurodevelopment. So one of the very first sets of macrophages that exit from that yolk sac into the embryo move into the area where the brain is going to be built. And that group of macrophages become the microglial cells. So microglial cells are really a form of macrophage, and they are doing the job of, and we talked about laying down the white matter tracks, making certain that the right neurons are being built, connecting the neurons together in ways that are functional. And then along the way in neurodevelopment, pruning away some of those connections that they made based on how sensory inputs and how activity is going on in the brain to make certain that you have the most efficient neural network functions. So that's what's going on up in the brain. But there's also a group of these macrophages that move into the liver, and they become what are called Kupffer cells, named after the man who found those cells. But those cells, like the microglial cells, last in that organ, in the liver, for your entire life. They are present. They may proliferate, they may reproduce, but they're there for your entire life to, as you said, maintain homeostasis. There's also a set of macrophages that move into the skin. At that stage, the skin is a few cells thick. It's the same kind of callous skin that we have when we're older, but that skin has Langerhans cells in it. Langerhans cells are a form of macrophage. Your kidneys have macrophages. Your spleen has macrophages. We've talked about this, the splenic macrophages. In fact, one of the reasons why we're having this conversation is we've had the discussion about what the cholinergic anti-inflammatory pathway is. And we talked about how at its base, stimulating the vagus nerve has the ability to downregulate the macrophages, take them from an inflammatory state to an anti-inflammatory state. So we thought it would be a really good idea to describe what macrophages are. But macrophages are really that construction crew, and ultimately through life, they're the maintenance crew, and how they behave and the things that they do are very similar across all of the different organs, are having these macrophages do similar things. Yeah. Things like clearing dead cells out, making certain that things are proceeding in an anti-inflammatory environment. Of course, they can become inflammatory if needed, but the goal is to not only become inflammatory, but also to bring everybody back to an anti-inflammatory state afterwards. So they're very exciting cells.
They are, absolutely. And when we talk about the macrophage here in terms of what it becomes through development, through our childhood and even into our adolescent and older age years, we're talking about this particular cell that I think has been misunderstood for quite some time. For the longest time in our conventional kind of thought process in Western medicine, thought of different systems as being completely separated and not intertwined with one another. We've thought of the immune system as being an area or a system that isn't exactly attached to or linked with other systems. We know that there are immune cells in all of these different organs, but it's never truly been researched to the level that it is or has been more recently. Now, you mentioned a few of these different types of what we call tissue resident macrophages. These are the macrophages that become resident or function within particular organs or things that eventually become these particular organs. Let's talk about during that developmental process, because I think we glossed over it just slightly at the end there. as these macrophages enter the different areas that are going to become different organs, such as the liver, such as the bone, they are actually there managing the construction of these different organs through that developmental process, through those 40 weeks of development. These macrophages are important and beyond important. If they're not present, the growth of these different organs doesn't occur the way that you're kind of hoping for. So let's dig into these a little bit. We've mentioned in the bone that osteoclasts are a form of tissue-resident macrophage. In the liver, we've got the Kupffer cells. In the lungs, we've got alveolar macrophages. In the brain, we've got microglia. We've got a whole bunch in the gut-associated lymphoid tissue. We've got particular macrophage activity going on throughout the entirety of the gut lining. But none of these organs would truly develop effectively if it wasn't for these macrophages. And what are the functions of these macrophages? Obviously, we're not going to go organ by organ and go through every single one, but in general, what does a macrophage do during that developmental process?
Well, it's coordinating first at the proliferation of the cells that are needed, because of course your liver has to grow, your kidneys have to grow, your lungs have to grow. That the process of the structure that they undertake ultimately form is guided by macrophages. So there's spatial coordination of the cell organization that is managed by macrophages. There are specific functions that are systemic, every tissue needs for homeostasis ultimately. Things like, and I know that we're planning to talk about this in a full episode, but iron. Iron is a critical element in our body's function, from everything from DNA synthesis to immune function to oxygenation, obviously, both internal in the cell and with mitochondria needing, not only needing oxygen, but also needing iron to function, to bone development. Iron is a critically important element, and the management of its metabolism, iron metabolism, is all coordinated by macrophages. So at each stage of the process of development, macrophages are playing a role. Now, I said before, the roles that it plays in the brain are different from the roles that it plays in the liver or in the kidneys or in the lungs. But by and large, it's using the same strategies. It's using the same tool set. It's using it in a different way, just the same way you can use a hammer to do 10 different things. The hammer is used, it's the common tool, but it's used in different ways for different purposes. We talked about, in the sense of the brain, we talked about things like coordinating the growth of white matter tracts. How does it guide that? How does it know that? How does it know how to do those things? Well, there's signaling proteins that it's using to align the tissue along these directional, both horizontally and vertically aligned tracks. It does the same thing when you're building bone. It does the same thing when you're building connective tissue. It does the same thing when you're building the structure of the liver or the structure of the kidneys or the structure of the lungs. The same signaling proteins are used. The same signaling proteins are used when figuring out whether to reinforce or support a tissue versus digesting it away and removing it. So we're using the same tools because Mother Nature likes to repeat using the same tricks once she's found that one of them works.
I love that. And it makes so much sense, right? We want simplicity, and the human body thrives on this idea of simplicity, that from the macro level, the breath is such an important controlling factor of the state of our body, whether we're in parasympathetic or sympathetic in terms of autonomic function, in terms of the coordination of how we respond to our environment accordingly, happens through this simple kind of task of being in a parasympathetic state, being able to observe, versus when necessary, being in that sympathetic state and being able to observe the risks and the threats and being able to respond accordingly as well. So having that same strategy present and simplicity present throughout the entire body makes a lot of sense. I think it leads to understanding the definition of even just the word macrophage in itself and why it was named the way that it was. Macro meaning big or large, and phage meaning eater, literally eating away, right? The macrophage can be broken down in linguistic manners to the big eater. And you can imagine, just in a very crude sense, I think is the way that I'm going to put this, when you eat enough and you do a little bit and you have your quote unquote portions controlled, you're able to maneuver and have good level of energy coming in, good caloric, good nutritional strategy going on. But if you start to eat too much and you take in more calories and not as much nutrient, then you're going to have some sort of dysfunction occurring. And this is where we can go towards kind of being in a homeostatic, anti-inflammatory or non-inflammatory state when we're following along with portion-controlled, clean, healthy diet versus when we're going on caloric binging diets. What we're essentially doing is we're going into an inflammatory state. In the same way macrophages will do exactly that. Let's talk a little bit about the macrophage in general and the processes that are involved in that big eating cell, big eating process.
Sure. So macrophages will identify on tissue that is either dead, and there's signals that it can see, and I use the word see, obviously it doesn't have eyes, but chemically see on cells that have died that they need to be basically debris cleared, that you need to clear out that debris. And it does it by basically wrapping itself around and digesting that dead cell. One of the signals, or the way it knows that, is that there's on living cells, there are certain chemicals, proteins, that sit inside the cell. And when the cell dies, they flip, and they're actually called flipases, which is sort of a great creative name to call them. But they're flipases that flip these chemicals around so that now on the surface of this dead cell or dying cell, and that is a signal to what they refer to as an eat me signal. So now the macrophage sees it and says, okay, I'm supposed to digest this cell away. It's dead or dying. We need to clear it out of the way so a new living cell can replace it. Those eat me signals are a clear signal to the macrophage as to what it should be doing. By the same token, living cells have on them don't eat me signals. And these signals are things that the macrophages can see, and they won't digest those cells away. Now, the size, I think you brought up an issue about, the size of a macrophage. Macrophages they're large cells, but there is a limit to the size of a cell that they can digest. Using the analogy of eating and overeating that you used, when we talked about white adipose tissue being inflammatory, well, one of the reasons why it's inflammatory when it becomes large is because the number of fat cells doesn't necessarily increase. It's the size of the fat cell that increases. And there's a limit to the size of a cell that can be digested away. Now, the problem is that when these cells get very, very large, they become difficult to maintain and they can die. They can become necrotic. And the problem is that the macrophage can't eat that large a cell without causing damage to itself. And so even when it eats just a piece of it, it can get damaged. What you end up having is a cluster of macrophages that's called a crown-like structure, because it looks like a crown sitting around that cell, of multiple macrophages, all trying to digest away that cell. Now, the process of debris clearance, or what's called phagocytizing that dead cell, is an anti-inflammatory process when done by that tissue-resident macrophage. So let me make certain that that's clear. We have a group of macrophages that are sitting inside the tissue. They came there from when you were in gestation. I mean, when you were a week or so old, the first wave of those macrophages arrived. They are tissue-resident macrophages that last for your entire life. Primarily, they're anti-inflammatory. Their homeostatic behavior of, even when they're digesting away those dead cells and clearing debris, is anti-inflammatory. When they encounter something that they can't digest away, or they're doing so much digesting away that it's pushing them into a more inflamed or inflammatory state, they will send out signals that recruit in a separate type of macrophage, a macrophage that we haven't talked about yet. So there's another class of cells called monocytes. And these monocytes are in circulation. They're part of your blood system. And when they're called into action, they will move into circulation and go to the site of that inflammation, and they'll move into the tissue, and they will become what are called recruited macrophages. They look similar, They do similar tasks during inflammation, but they're not by nature anti-inflammatory. By nature, they're pro-inflammatory. So when they're called into action, it's because they need to be inflammatory. They come in and they start doing damage. So when we talked about people who get themselves to a state of having lots and lots of white adipose tissue that's very enlarged, you'll see a lot of these recruited macrophages moving into the tissue. They're inflamed and they're trying to help the resident macrophages digest away these cells that have died. Problem is that in the process, they can actually become inflamed themselves and they can die. And we talked about it in the context of atherosclerosis, that macrophages that are eating things that have lots of fat in them and cholesterol in them, which is what your adipose tissue has, will become foamy looking. And when they get too foamy looking and there's too much going on inside them that's lipid based, they'll die themselves. And so you have this constant inflammatory state that's very difficult to undo, which leads to metabolic syndrome, which we've discussed before.
Yeah, so this makes a lot of sense. Understanding that the tissue resident macrophage, in its general sense, is anti-inflammatory. It's pruning, it's cleaning, it's a maintenance crew that takes up residence within that particular organ, within that particular tissue that it's in. And those are necessary for maintaining the function of that particular organ. In the same way that we have a security team in a building that's been built, in the same way that we have a maintenance team and the team that manages the trash and manages the cleanliness of a bathroom in a skyscraper that we've built. We have all of these particular roles for these important things that if they weren't present, the function of that skyscraper or the function of that building would be compromised significantly. And that's where the tissue resident macrophages come up. When there is a massive issue, when there is some sort of concern, where there is some sort of challenge that needs to be taken care of, they will then recruit external help or external support in the same way that a security team would call the police to come and help support some sort of security breach that's occurring within the building. Or if there's a massive plumbing issue that's going on within the building, they're going to have to call an external plumbing team to support if there's a big leak or something going on within the janitorial team, for example. So the recruitment of these external supports doesn't really care for maintaining the current or the optimal status of the function. They're simply there to put out the fire, or that's their intention, is to help to put out the fire. The control of that is what's really important. When we are in a pro-inflammatory state for a short period of time, for example, the firefighter comes to put out a fire, they're not truly concerned with making sure that 3 weeks down the road that area is not completely damaged. They just want to ensure that in that acute scenario that the damage is contained and that there isn't widespread damage that can occur, versus the tissue resident macrophages who then have to come back in and rebuild that damaged tissue. They will care more about the maintenance, right? So understanding the difference between the maintenance team located on site versus the recruitment of other teams that help support in an emergent scenario.
Absolutely. And sometimes, especially if that inflammation lasts for a long enough period of time, even after the monocytes that have turned into recruited macrophages have sort of either left the scene or died out, because they don't last anywhere near as long as the tissue resident macrophages. The resident macrophages last your whole life. The recruited macrophages last for a matter of weeks.
Yes.
Even after they're gone, however, if the inflammation has lasted long enough, the resident macrophages can be affected by what's happened. So it's not just that the tissue has been damaged, it's actually the resident macrophages themselves have been changed in a way that you hope that you can get them back all the way to where they were. But sometimes they stay in a state that's primed. We talked about primed microglial cells that exist in your brain after a traumatic brain injury, a concussion. They remain in that hypervigilant state for an extended period of time. And because they're in that hypervigilant state, you're prone to real problems if you have a second injury, because they're already overly active. But they also can lead you to have ongoing headaches, ongoing mood problems, ongoing cognitive issues. They can, in the long term, if they stay primed for your entire life, they can lead to long-term degenerative problems in the liver or in the kidneys, for example. When you have that long-term inflammatory state that's shifting those resident macrophages, not the recruited ones, but the resident ones are getting shifted, they can end up causing fibrosis in that tissue. And in the liver, for example, fibrosis leads to damage of liver function and ultimately to cirrhosis, which can be lethal. And actually, cirrhosis typically does end up requiring either a liver transplant or you get cancer or die. And so it's really important to find ways to shift those macrophages, those resident macrophages, back into that truly anti-inflammatory homeostatic state that you need, and not to remain in a state that, while not being overtly inflammatory, it's not functioning properly.
So this is where we get into a lot of the chronic health conditions that a lot of people are experiencing. Things
Yes.
like the non-alcoholic fatty liver disease, NAFLD, in a metabolic state that is inflammatory. Metabolic inflammation will lead to excess inflammatory activation of the Kupffer cells, of the tissue-resident macrophages in the liver, leading to excess fatty acid buildup within the liver tissue. That will compromise function, and done for a long period of time, or even in a state of like alcoholic inflammatory activation, the liver will become fibrotic. It will become broken down due to the shift of the tissue resident macrophages, the Kupffer cells, to an inflammatory state. And these tissues are laying down fibrous tissue to help support structure of that organ, but not necessarily to maintain function of that organ. And that over time, down a chronic longer term path, can lead to, like you mentioned, cirrhosis of the liver. So it's a really important thing to understand that these tissue resident macrophages, when given the right inputs, when given the correct environmental inputs that are generally anti-inflammatory or lower on that inflammatory scale, they're going to maintain homeostasis. They're going to maintain optimal function in those organs. When the signaling or the environment causes low-grade, continuous, long-term inflammation, then these tissue-resident macrophages can be turned into pro-inflammatory macrophages that may not be primarily concerned with the function of those organs and can actually lead to breakdown of those organs.
Yeah, it's not always pro-inflammatory though. It actually causes a dysfunction in the macrophage to revert to a developmental state. So we talked about this in the condition of Alzheimer's when we were talking about the same types of things happening in the brain, where you're absolutely correct that long-term inflammation can convert these tissue resident cells into an inflammatory state, but it's also, in some cases, even more so damaging when they're tricked, if you will, or induced into returning to a developmental state where they're doing things that are appropriate for the development of the organ when it's growing, but not when it's fully grown and in a homeostatic state. And so fibrosis is an example of one of those things where, yes, you need to build the scaffolding and the structure and build the organization of the liver itself. And that involves connective tissue and other things that are laid down to just have a structure around which the liver can be formed. But when you have damage done to the liver, when there's a liver injury, an acute injury, then those tissue resident macrophages can employ the same tools, employ the same strategies that they did during development to try to restore that organ to its state. And that involves laying down of connective tissue and scarring. In fact, scarring really is, in some measure, a return to a developmental state, trying to restore the tissue to the state that it was prior to the injury by using those same tools that it used when it was creating that tissue to begin with. And sometimes that's appropriate. Even in the skin, you see scarring. But in organs, you can see scarring where there's extra fibrosis, there's an extra thick level of structure that's built, and that can damage or replace the tissue that needs to be there in order to perform the organ's function. And that's what we're talking about in the case of cirrhosis of the liver, but it also happens in the kidneys. It can happen in the lungs. It can happen really in any tissue where the macrophages in the process of trying to heal are employing the wrong types of tools.
We've mentioned this particular inappropriate tool being utilized in the brain. Do you want to just do a little bit of review of microglial activity when it is inappropriate?
Sure. We talked about this in the case of Alzheimer's. One of the things that microglial cells do during neurodevelopment, so in the early stages of life, they're involved in first synaptogenesis, so they're causing lots and lots of synapses to be formed. And then through early childhood into really, frankly, up into your teens and 20s, when your brain is still developing, what it's doing is it's using this ability to prune away cells that or connections that it doesn't want to have be present in a sensory and an activity dependent way. Those tools need to be pared back. If they don't settle down in their robustness, then you end up with too few connections. And we talked about that in the context of schizophrenia. But then later on in life, when you get to be 70, 80 years old, if as a result of a lifetime of stress and potential injury and inflammation, your microglial cells start to revert back to that developmental state, they'll begin to become overly active in their pruning. Now, one of the things that we talked about is, well, how do you prevent those microglial cells from staying in that hyperactive or dysfunctionally active state of pruning away too much? Well, it is using the tools of neurodevelopment, which are sensory and activity dependence. So one of the things that you can do to stave off that process or to slow that process is to remain active intellectually and emotionally and getting socially engaged, getting involved in doing crossword puzzles, doing puzzles, going on walks, getting involved in the local play, getting a part-time job, things like that that keep your mind active will prevent that activity that's really appropriate during neurodevelopment, but not appropriate later. That's one way you can do it. A technique that's being investigated right now is what's called microglial depletion or ablation and repopulation. And this is we'll go into a little bit more detail than we did last time about this. This is literally using chemicals that are known to kill off your macrophages. So in the case of the microglial cells, you would use a chemical in the central nervous system that when you deploy it, it blocks something that's absolutely required for microglial cells to exist. And so within a very short period of time, you can kill off 90, 95, 99, even more than 99% of the microglial cells. So you stop them from doing what it is that they're doing. Now, that's not a healthy state to remain in. But fortunately, these tissue-resident macrophages, or in the case of the brain, the tissue-resident microglial cells, have the ability to replenish themselves very rapidly. So when they sense that their population has dwindled, they will repopulate themselves. They don't need to call in any cells from the outside. They can do it right in the brain itself without needing to bring in those recruited macrophages. So these are resident macrophages that are repopulated from what's already available. Now, it's very early days in terms of the techniques and whether this therapy would be successful. But the idea is that by killing off 99% of the cells, it's possible that the remaining ones may still be healthy and functioning in the appropriate way, or that when they differentiate, they repopulate into that baseline anti-inflammatory state that will not be exhibiting that dysfunction. Lots of different interesting ways of approaching it. The way that we've talked about a lot is that the nervous system, the autonomic nervous system, has a way of regulating macrophages, which is this cholinergic anti-inflammatory pathway. The central nervous system, in conjunction with the autonomic nervous system, has the ability to trigger the release of acetylcholine, and acetylcholine has the ability to tell these macrophages, whether they are resident or otherwise, but we're talking specifically about the resident macrophages, to shift into a quiescent state, not a state that would be destructive. Now, There's still a lot of work to be done to see how that can be used therapeutically, but it's certainly very promising as a non-invasive, non-destructive way of utilizing what the body's own systems would do to regulate microglial or macrophage activity in a positive way.
So this is a great way to kind of understand that we actually do have neural control over immune cell activation, both in the tissue resident state or in the tissue resident cells, as well as even in circulation to some extent, that there is a connecting point between how the immune cells are turned on, the state in which our body is in, our neurological activity is creating this messaging to particular areas, particular cells, or systemically that can shift the balance of these tissue resident macrophages. And if in a state of homeostasis, we are generally in a state of parasympathetic activation. We're generally in a vagally activated, I'm talking about the vagus nerve here, vagally activated parasympathetic rest, digest, recovery, homeostasis, balance mode. And we don't need to be there 100% of the time. In fact, if we are there 100% of the time, we're not utilizing the tools that are available that we might want to use in a controlled sense from time to time. And I'm talking about activating the sympathetic nervous system, essentially turning on stressors hormetically. So I'm talking about hormesis, hormetic stressors. These are things that actively create stress within the body, but only to be able to shift our body from parasympathetic to sympathetic in a controlled sense. It's almost that controlled burn. Let's talk a little bit about hormesis and how it likely creates a bit of a shift in the activity of these cells and allows us to be able to shift between sympathetic and parasympathetic. We don't need to get into it deep, and I know this wasn't something that we kind of mentioned talking about before, but I think this is a great segue into understanding it.
Sure. And you mentioned something just before, before we leave it, the macrophages that are in that developmental state are regulated by the autonomic nervous system. And so it's not simply that our autonomic nervous system and our central nervous system has the ability to shift us into that rest and digest mode versus the fight or flight mode. It's not simply the shifting back and forth. It's literally changing how our bodies develop. So we've seen in research that a stressful environment has effects on the central nervous system. Growing up in a stressful environment where you're either subject to lots of physical stress or emotional stress or not getting the right nutrients, et cetera, can literally change how your brain and body develop. It's sort of obvious. It's sort of like just understanding that if you don't have a nurturing environment, both physically and emotionally and mentally, your body and brain won't grow properly. That literally can be controlled by the central nervous system to a very large extent. Obviously, you can't make up for not having food, but what you can make up for is by having the right mindset, you can literally change how you become, how you grow. And that's obviously difficult for children, but it's difficult if they have to do it consciously and have to figure out how to do it. But if there's a way to, and we talked about this in terms of neurodevelopment, but it's also for physical development. If you can reduce the inflammation state and allow those macrophages to be in their most developmentally focused state, you will have the most robust physical development. And we know this. We know this already because we know that inflammation, stressful environments are destructive, even in terms of how tall a child is, how strong the child is, how emotionally stable the child is, how intellectually capable the child is, and even in the long run, how long that child will live in terms of the lifespan and how healthy and pain-free that individual's life will be. And we talk about, we don't just want to increase the lifespan, but we want to increase the life in that span. I think it's really important for people to understand that the role of the macrophage and the interplay with the central nervous system isn't simply to suppress inflammation in adulthood or inflammation or prevent degeneration as you grow older, but literally in development, early on in development, becoming everything that you can be to live up to your potential, if you will. it requires minimizing that distraction of inflammation and letting the macrophages that are literally building your body do the best job that they can.
I love what you said there, and I just want to mention a couple of things here. So you mentioned extending not just lifespan, but life within that span, something that I refer to as health span. So your lifespan may be literally the time from your birth till your death, and expanding that matters. We want longevity. We want to live as long as possible generally. But for a lot of people, there's a gap between their health being optimal or being allowing them to remain in a very optimal functioning state. That gap may end where their health deteriorates to the point where they're no longer a productive member of society, unfortunately. And that gap between when their health deteriorates and their lifespan ends can often be a point of contention, a point of challenge for a lot of people. So what health span is can we extend or decrease the gap between where your health deteriorates and your life ends? And I think that's a great way to kind of understand that.
In Europe, and actually in the United States too, but it's more well known in Europe, they use something called QALYs, which are quality of life years. So to your point, what you want to do is you want to extend the number of years in which you have 100% use of your body and 100% use of your faculties for as long as possible. You want to maximize not only your lifespan, but you want to maximize your QALYs, your quality of life years. And to the extent that you can do that by making certain that right at the very beginning of life, in the first few years of development and growth, you have done everything you can to minimize the challenges and influences and effects that you have on that development, you will then see how that reap benefits all the way through life, even into your 90s and beyond. You want to be able to have that maximum quality that is really the foundation is set in the very beginning. It's like building that skyscraper. If you don't build the foundation right, you can't have the building go all the way up to 100 stories. So I wanted to give you the opportunity. You brought up hormesis. I wanted to throw it back to you and say, what was it that you were hoping that we would tackle with that?
Yeah, I think with regards to hormesis, I think what I was kind of mentioning is that the sympathetic state can often be vilified in a negative or given a negative connotation, that we don't want to go into that sympathetic fight or flight state too often, and that it can often be negatively viewed. But what I want to mention there really importantly is that the sympathetic state is required for our growth in these challenging environments. And so you mentioned stress. And so I want to talk a little bit about how I got to the hormesis thought point. And that is when you mentioned stress is negative or it's chronic or it's too severe for our ongoing growth, that can be called distress. I was turned on to this by Tim Ferriss. One of the first audiobooks that I listened to was 4 Hour Workweek. And he mentioned the difference between distress and eustress, EU stress. And this is what hormesis versus negative stressors kind of leads to. So distress is when the fire is constant and it's on all the time and it's just too much. It can be emotional, it can be psychological, it can be physical, it can be biochemical in the state of nutritional deficiency. Where something like hormesis, eustress, where a little bit of this stress controlled under certain circumstances can actually be very positive for the growth of the person. The difference between being starved for multiple days versus fasting, right? A controlled experience of some sort of stress that allows for our shift from parasympathetic to sympathetic, but being able to shift back to that parasympathetic in a controlled manner. In the same way that a farmer will burn a certain area of crop to allow for the nutrients to be re-engaged with the soil, but it's a controlled burn, and then they're able to actually grow more and healthier crop in that particular region after the stress, after the fire has been created. Goes towards exercise as well, right? Like straining the muscle to be able to build it and to grow it. We know muscle generally being the organ of longevity in reality. If we lose our muscle, we can't maintain our physical posture, we can't maintain our physical strength, we can't maintain longevity. Dr. Gabrielle Lyon is a big proponent of this, being muscle being the organ of longevity. And what is essentially pointed out there is if you don't use it, you lose it. If you don't move your muscles, they will deteriorate. And as they deteriorate, your health span will decrease accordingly. And so this is that importance of staying, to some extent, active throughout the entirety of your life to maintain that hormetic stress, but allow you to shift back to that parasympathetic state.
Absolutely. The last thing you just said reminded me of a great Nike ad from, I think, the late 90s, where they had these very old people, and by very old, I mean in their 90s, that were still very vigorously exercising. One advertisement had a man who was in his mid 90s who was still very, very strong. You could see he was what my kids would refer to as jacked. He had, lots and lots of muscle. He had been weightlifting, and his line was, "I am not strong for my age, I'm strong." And there was another one in which there was an elderly woman who was out running, and she said, "I may be wrinkled and gray, but I am not old." And so I totally agree with you about the importance of exercise and muscle as a means to extend not just your life, but your quality of life years. Now, to the point of acute stresses and how acute stress can actually facilitate the transition back to that homeostatic rest, digest, and restore mode. We did some research with a researcher over at University College London. He was interested in acute kidney injury. And so in the model of kidney transplant, so in the process of removing an organ from a donor into a person who needs a recipient, there's tissue damage that happens to the kidney. And you want to minimize that damage that happens so that the individual, the recipient, can have a functioning organ that they need to survive. What was found was that prior to the transplant occurring, if you caused a hypoxic event, a temporary hypoxic event, cutting off the blood supply to the wrist, putting something tight, a tourniquet around the wrist so that the hand would go through a period of lack of oxygen, that there would be a stress associated with that. And that hypoxic stress would then trigger an inflammatory response. Temporary, you could relieve it within, an hour, and blood supply goes back. That if you did that at the time of the transplant, that the transplant would experience much, much lower acute kidney damage. And so the AKI, or acute kidney injury, would be less by about 50%.
Wow.
The interesting thing was that individual who had that hypoxic event occur didn't necessarily have to be the recipient. It could be the donor. You could do that with the donor prior to removing the kidney, and then the benefit would accrue to the recipient. You could do it with the recipient also, but it was very curious that you could do it on a body part that wasn't being transplanted. You could cause that hypoxia somewhere else in the body and get the same benefit. And I think that goes to, you've signaled to the entire body that there's a pro-inflammatory event, and then afterwards, your body will benefit from it. We see this in our own lives. We talked about this, that exercise for a short period of time, it can be mental exercise. It can be some stress that you have at work. When you have that stress for a short period of time and then you relax from it, the relaxation is more meaningful. You actually restore yourself more if you've stressed yourself prior. You don't get the same benefit. In fact, too much rest can actually be damaging. We're learning right now that, sitting is the new smoking. If you're not up stressing yourself, if you're not building muscle, if you're not using it, you will cause yourself to have more damage. And in fact, fibrosis, you can rid yourself or reduce fibrosis by simply being more active. So I'm glad you brought that point up. It's an excellent one.
Yeah, I think it's an important one when it comes to understanding resilience, right? And that's what this is those acute stressors of sympathetic hormetic stress activation, eustress, EU positive stress, allow for your body to learn how to shift back to parasympathetic more readily. And in doing so, the same way that we create that hypoxic event, pre-surgical intervention, pre-transplantation, we're creating this environment and this understanding within the body that here's a stressor, B, here's how you recover from it. Now, when we go through this new stressor, you're going to likely be able to recover from it because you already have a pathway drawn out. It's like literally by doing this eustress type of movement, you've cleared a path for that recovery to then potentially occur if a new stressor were to come along. And now you are actively stressing the kidney by transplanting it from donor to recipient, and the recipient receives that benefit because that kidney is able to go through that pathway that's already been cleared by the previous stress event.
Correct. And one of the things, just to follow up on the research that was done, the idea was to mimic that stress and then restoration shift without needing to provide an actual physical stress to begin with, but to simply stimulate the parasympathetic nervous system. In the case that we were working with, it was with vagus nerve stimulation, using electrical stimulation of the vagus nerve to benefit the transplanted kidney in the same way without having to do the prior hypoxia to trigger it. So you could trigger it simply with vagus nerve stimulation, and the results were very positive. It was an animal model. It's obviously very early on, but I know that work has continued at with multiple different researchers looking at the use of parasympathetic activation as a way to gain that same benefit.
And for a lot of people, the concern is not necessarily with, I think the focus needs to be on being able to shift from the sympathetic back to the parasympathetic. And in certain cases where vagal tone is limited, we're having difficulty shifting back to that parasympathetic state. And that in itself, that shift is what I call resilience. It's that ability to shift from stress to recovery, to that rest, digest, recovery state. And for a lot of people, that's where vagus nerve stimulation can come in really handy and potentially really effectively. And from a foundational practices type of manner, we can talk about things like deep breathing, Gregorian chants, things like that, that are vaguely activating, very resilience building. And unfortunately, not enough people practice these types of things. And we tend to go into this sympathetic state way too easily. We live in an environment that is biochemically, environmentally stressful. And now in terms of finances and emotions and all of these things, people are experiencing major stressors, and that's shifting us into that sympathetic state more often than not, and not allowing that resilience to shift back to vaguely activated parasympathetic state. And what that then is doing is going back to the macrophage activity, it's actually allowing those macrophages to remain in a slightly more pro-inflammatory state, where they're actually doing a little bit more damage and recruiting a little bit more of these external macrophages on a regular basis. And that then leads to chronic disease processes. I think just bringing it back to the macrophage, vagus activation is going to shift macrophage activity to an anti-inflammatory state, where vagus downregulation is often going to allow for macrophages to remain in a pro-inflammatory state. And that's where I think therapeutically, the vagus nerve is one of those areas that we can really positively affect, that'll allow for a lot of these disease states to be potentially reversed.
I think it accelerates the process of getting yourself back to the point where you can take that stress again. The issue that you bring up about Western society and how we have sort of a chronic state of sympathetic pressure being applied to us is absolutely true. And one of the things that we need to do is recognize that simply recovering enough to be able to go back into a stressful environment isn't enough.
Yeah.
What you really need to do is embrace the stress while it's there. Use it, do what you need to do, accomplish the task you need to do, but then break away and have a sufficient time to restore yourself. Because if you don't restore all the way, then what's happening is those macrophages and the microglial cells in your brain, they're going through that eustress. They're going through that eustress, but then because they don't get the chance to fully restore back to where they're in that restorative, neurotrophic, in the case of the brain, or physically homeostatic state, they don't get all the way there. Then that eustress that's good starts to become, after a while, repetitively becomes distress because you're never getting away. I think we've all experienced that. You can handle stress with your kids. We're going through it right now. It's the end of summer break. The first week out of school, it's great to have the kids home. You get to sleep a little later. You don't have to worry about getting them off to school. You get to spend time with them, have fun, enjoy their laughter, all that sort of thing. But by 11 weeks into it, you're thinking to yourself, I can't wait till these kids go back to school, because you need to get back to it being great to see them at the end of school, great to see them on the weekends, but you get that chance to restore a little bit away from it. And I'm not suggesting my kids are stressful, but I think any parent will probably be laughing, and as you're smiling about it too.
I'm very significantly smiling about it right now. It's quite the large smile. And I remember you mentioned a funny ad, or an ad from Nike. I want to mention that in Canada, we have Staples, Business Depot Staples. It's our version of Business Depot over here. And they had an ad that went on for years. And it was the song, It's the Most Wonderful Time of the Year, when back to school was going on. So I absolutely understand that. It's like we can finally kind of get back to some level of, being able to work and
Homeostasis.
have our homeostasis. I love it.
Yes. So the vagus nerve stimulation the goal is to accelerate that process of getting back to homeostasis. And sorry for breaking up the fun, but get back to what happens in the central nervous system when you have a concussion. And so we all watch in sports as, some player has a concussion, and we wonder how quickly is he going to get back to the game? How quickly can he get back into playing? Because we want to see that star on the field or on the court or wherever. And what science tells us is that, yes, it's true, the individual will be able to function back to close to normal within a week or two, probably 2 to maybe, sometimes if it's really bad, 3 weeks. They're back on the field. But what's happening in that brain is that those immune cells, those microglial cells, have not gotten back to that homeostatic state. The brain is functioning. The damage that was done, the shear force damage, et cetera, structurally has been restored. But that doesn't mean that the immune cells have quieted back down to their homeostatic state. And as a result, they remain in this vigilant state. And if they're stressed too much, they can become inflammatory chronically. And that's very damaging. That's exceedingly damaging. And that's where you see things like CTE and mood changes and chronic pain and sleep disorders, and even, frankly, mood and cognitive function that's really disturbing.
Yeah.
That all of that happens as a result of not allowing that eustress to become homeostatic. It becomes distress. And so it's really important, again, we've talked about it before, but really important to ensure that you've gotten back to that state where the microglial cells are back at homeostasis before you put it through the kind of stress that an athletic event and injury might cause again. The good news is that parasympathetic activation can accelerate that process of getting those cells, in the case of the brain, microglial cells, in the case of macrophages in the body, back to that homeostatic state faster. So if you've experienced some sort of inflammatory event or an injury or something where there's a possibility of those macrophages pushing a fibrotic state that's beyond simply the necessary scarring, but overly scarring and causing problems with the organ function. If you want to get those macrophages back to that state more quickly, parasympathetic activation, exercise, stretching, doing the things, deep breathing, potentially using a stimulator of some sort, doing something to accelerate that restoration back to that homeostatic state is critically important.
I couldn't have said it better myself. And I think this will lead to, potentially a future episode on concussion, CTE, mild traumatic brain injuries. I've had numerous patients and numerous interactions with people that have experienced mild traumatic brain injuries, whether from whiplash or from concussion. And the effect of vagus nerve stimulation has been shown to be really, really beneficial. on a case-by-case basis, but we're seeing really positive results with regard to affect, with regard to mood, with regard to digestive function and overall inflammatory activation through the body. People feel often like they're able to return to a significant state of functioning where they're not burdened by the stressors of what had happened in the past, and their brains actually start to work better again, which is quite wonderful. So I think at some point we can definitely dig into that particular topic in a full episode.
Well, the fall has the return of school, but also the return of a lot of sports that have the possibility of those kind of injuries occurring. Obviously we know about the possibility in soccer and in football and in hockey for collisions that can lead to concussions. And so it's important to get that information out to people and treat concussions very seriously. Yeah. It's not something that just because the player was able to get up and walk off the field doesn't mean that the player is ready to go back, the next play.
Yeah, the timing is very interesting. I just read the article about Brett Favre stating that he likely had thousands of concussions through his career. Every time he was tackled, every time he took a hard hit, and there was a bit of ringing or some bright lights, every single one of those was likely to some extent a concussion or a traumatic brain injury. So it's a really important topic that it's becoming more forefront, but each one of those is a very significant stressor on the body and can lead to negative function changes for sure. So
absolutely. And we hope that there's going to be therapies that will allow these players to get back and play the game that we all love to play and to watch and to enjoy, but we want to make certain that doing it in a safe manner. And that one of the things I hope for is that someday there will be a protocol that involves activating the parasympathetic nervous system in order to, as a therapy for concussion.
Yeah,
I think that's in the works at some point. We're going to see that, and I think it would be wonderful because, as a good friend of mine once said, from the time that we watched somebody fall out of a tree and get a concussion from 10,000 years ago, 20,000 years ago, we knew that the person wasn't right. We could tell that the person had been concussed, but really has been impossible until very recently to do anything about it. Mm-hmm. And now that we have that, the potential for a therapy to benefit them is really exciting.
Absolutely. I think this is a great place to end our discussion on macrophages and obviously the importance of allowing for them to remain in that optimal homeostatic state where possible and teaching them to remain in a productive fashion so that our health span can be given that longevity that we look for ideally. So this is a wonderful place to end our conversation today. Any parting words?
Just be aware of the fact that the macrophage is building you. The macrophage is maintaining you. The macrophage is going to be ultimately, if you don't take care of them, the cause of your demise. Care for them well and make certain that they have the best opportunity to give you the best life you can have.
I love it. Thank you so much for listening to today's episode. JP, thank you for joining me again. And if you like this episode and you want to learn more, please continue listening to a few episodes of the past that discuss a lot of these topics in detail. And we will continue to bring you more and more of these exciting topics of how we can upgrade our health by taking a look at all of these different cell types and actively affecting our shift to a parasympathetic recovered based state. Thanks for joining and thanks for listening. And please share this with anyone who needs to hear this. Have a wonderful day.